Today I'm going to talk about decision analysis, specifically how to set a target for environmental policy. I'm mostly going to talk about cost-benefit analysis in 3 chapters, stock and flow pollutants, and then uncertainty. Then I'm going to talk a little bit about alternatives to cost-benefit analysis. And then I'm going to return to cost-benefit analysis and talk about its application with an example from the London super sewer. And this is lecture 3 in the series. This is where we are. Robert Solow wrote, economists have the reputation of being unimaginative bean counters, doggedly claiming to quantify the unquantifiable and personifying Oscar Wilde's definition of a cynic as someone who knows the price of everything and the value of nothing. It is true that they, economists, would give a lot for a rough quantitative answer, but it only reflects the fact that any policy can be pushed harder or less hard, further or less far, and that a useful evaluation has to suggest how hard and how far. The beans have to be counted, if only approximately. This is essentially cost-benefit analysis, but Solow being Solow, then puts the but in. Those gentle souls who merely ooh and ah over them are arguably part of the problem, not part of the solution. Rather lengthy definition. Abraham Lincoln had a more succinct definition. The true rule in determining to embrace or reject anything is not whether it have any evil in it, but whether it have more of evil than of good. Which is a bit outdated in its use of English, but fairly captures cost-benefit analysis. Johan Cruyff, of course, had the most succinct version, and that is that every upside has its downside. And that is what cost-benefit analysis is about. It's about counting the upsides and weighing them against the downsides of any policy intervention. Obviously, if there's a policy that has no downsides, then we don't need to talk about it. We just need to do it, right? But it is when there's winners and losers, when there's good things and bad things about a particular policy, then we actually need to start thinking about whether to do it and how hard to push it if we do. We're obviously going to talk about pollution, and just to recall the definition of an externality. Pollution is an externality, and it's the unintended and uncompensated impact of an economic activity on a third party. But there's more that we need to know about pollution, because pollution also depends on what is going on in the natural environment. And if you want to understand what is going on and you want to solve it, and in order to solve something you need to understand what you're trying to solve, you also need to know a little bit about atmospheric physics and chemistry and biology. And an important part of that is transport, transformation, and assimilation. Whenever you dig up coal, whenever you look at a piece of coal, then you would always find that there's a bit of sulfur contained in that coal. Now that is perfectly innocent as long as it's contained in the lump of coal. However, if you burn that coal, then that sulfur gets oxidized to sulfur dioxide, and sulfur dioxide again is perfectly innocent. But if sulfur dioxide in the atmosphere meets more oxygen, then it turns into sulfur trioxide, which again is still perfectly innocent, but only when it gets into contact with water does it become sulfuric acid. And sulfuric acid is harmful to all organisms. This is one of the main causes of acid rain. It kills trees, it kills fish, it damages monuments that are built of limestone, it affects human health, and so on and so forth. So it's only after it's been chemically transformed 3 times that the sulfur becomes harmful. So that is the first thing to note. Sulfur in itself is not bad, but it's only in a particular chemical constellation that sulfur becomes problematic. The process of the combustion of the coal to the deposition of the sulfuric acid takes time. This is not instantaneous. This typically takes 1 to 4 weeks, where 2 weeks is sort of the modal deposition time. In those 2 weeks, sulfur travels through the atmosphere, and sulfur that is emitted in England rarely ends up in England. It gets blown, because the wind is mostly from the west, it gets blown to the continent of Europe. So it is an externality that crosses borders depending on the direction and the strength of the wind, right? It obviously creates problems in solving it, because the acid deposition, say in Denmark, may be to a large extent due to emissions in England, and obviously the Danish authorities have no say over how we burn coal in this country, right? So that creates a problem for its solution. There's also a good bit of sulfur that ends up in the English environment, and that is the reason why we clean it up, but also a lot of it crosses borders. And that was particularly a problem across the Baltic, where a lot of stuff from the former Soviet Union ended up in Finland, and because of the antagonistic relations between the countries, there was very little that the Finns could do. So those things are important to know, right? Because that is how that shapes how you would solve it. Obviously, the background concentrations, the existing load also matters. If you add a little bit of sulfuric acid to an otherwise pristine environment, nothing much bad happens, right? If you add a little bit extra sulfuric acid to an ecosystem that is completely degraded, nothing bad can happen, because everything that is bad has happened already, right? But in between, additional sulfur can actually do a lot of damage, right? So little damage if the environment is pristine, a lot of damage in the middle, and then little additional damage if the environment is a complete moonscape, right? So that also matters how seriously you should be working on solving this particular problem, right? The two extreme cases that I'm going to talk about are flow pollution and stock pollution. Flow pollution is the case when, as soon as the activity that causes the pollution stops, the pollution stops as well. And the canonical example here is noise. 6 in the morning, your neighbor leaves for work, starts his engine, wakes you up, right? But as soon as the car is out of the street, the noise is gone, right? So the pollution is no longer there. You may still be annoyed, but the pollution is gone, right? The canonical example of a stock pollutant is nuclear waste. Some of the radioactive material that is generated by nuclear fission, it has lifetimes that is measured in hundreds of thousands of years, tens of thousands to hundreds of thousands of years. That means that if we stop using nuclear power today, then the problem of nuclear waste will still be with us 50,000 years from now, right? So that is the difference between flow and stock pollutants, and obviously there's mixed forms as well, but that does not generate additional insight. So let's look at efficient flow pollution and what we would do in a cost-benefit analysis. So I'm going to do this first mathematically and then graphically, and I'm going to interpret it all along the way, right? So I assume that there's damages of pollution and they are denoted by a function d of pollution m, where m is the m in emission, right? The benefits of a polluting activity I denote by b, and that is also a function of m. So the net benefits are how much you gain from the polluting activity minus how much damage you do. So that's b minus d. And then what we would want to do is maximize the net benefits. You can also minimize the net cost, but that is of course the same thing. So what do? We take the first partial derivative of the thing that we want to maximize, the net benefit, to the thing that we decide on, that is emissions m. So we take d and b dm and set that equal to 0. D and b dm, or d and b dm is it's just b minus d, right? So that's db dm minus dd dm. Does my cursor work again? Yes, my cursor works again. So it's db dm minus dd dm must be equal to 0. We bring the ddm to the other side of the equation, and what we have as a first order condition for optimality is that the marginal benefit of emission control equals the marginal cost of emission control. So this is a very simple equimarginal principle. Graphically, so my cursor works again, but now the thing doesn't want to move on, this is your gain from polluting activity, right? If you do nothing, there's no gains. If you do more, you get happier, your utility goes up. But at a certain point, utility comes down. Now, why would this be? Think of energy use. You can heat your apartment, and at the moment it's not that cold, but a few weeks ago it was very cold, so you probably did so, right? Because it was uncomfortably cold in your place. And you can heat it to 14 degrees or to 18 degrees or to 22 degrees. But the more you heat it, the more expensive heating becomes, right? You can heat it to 26 degrees, but that is actually for most people an uncomfortable temperature. You can heat it to 30 degrees, but then you're just spending a lot of money, and I don't think that 30 degrees is very comfortable for an apartment to live in, right? That's my opinion. Some people disagree with me there. But at a certain point the place becomes uncomfortably hot, and probably well before that time it becomes too expensive to justify the additional heat in the house, right? So at a certain point you stop heating the place, right? Because it gets uncomfortable, because it gets too expensive. Similarly for travel, you go to the place where you need to be. You don't take a big detour on the way, because that costs time, because transport is expensive. So at a certain point you reach your destination and then you stop traveling, right? So also there is sort of like at one point you stop polluting as well, because you do not, pollution is an externality, right? This is not the purpose of your action, this is a byproduct of you traveling, this is a byproduct of you heating your apartment, right? So at a certain point you stop, and at that point, or that is at the point where your utility of doing more goes down, right? So you can see that that's the point where the curve reaches its optimum, Q prime, which is the same as where the marginal, the slope of the curve, goes to 0, right? So that is the first step. Now there are also losses, not because it's an externality. Those losses do not happen to you, they happen to other people in society, and they are strictly negative in this particular example. That's the green line. So now instead of wanting to maximize the private gains, the brown line, we want to maximize the sum of the private gains and the social losses, and that is the red line that you see here. And those would be the net social gains from emissions. That's the difference between the private gains of the polluting activity and the social, the external losses of the polluting activity, right? So how do we find the optimum of the red curve? Well, essentially we want to see where the slope of that thing goes flat, right? Where essentially the first partial derivative is 0, which just happens, no, not just happens, which is equal to the place where the marginal costs, the slope of the brown curve, equals the slope of the green curve. Now flipped, I flipped one of the two curves. I flipped the green curve because if you recall the derivation, the net benefits, first partial derivative, the net benefits should be 0, and that means that one of the two elements need to be brought to the other side of the equation, right? That is why I flipped the green curve from negative to positive, right? So the point where the marginal net social gains hit 0 is the optimum, and that coincides with the marginal private gains from the emissions equal the marginal social losses from emissions. That is how we would set a target in a cost-benefit analysis in a flow pollutant, right? I'll come back to the stock pollutant in the not too distant future. So this is the same curve again. The 4 areas that you're looking at, A, B, C, and D, all have an interpretation. Area B is the optimal level of environmental damage. Area A plus B is the optimal level of the net private benefit to the polluter, right? So it's not that we're sort of banning environmental pollution, and we're actually allowing people to continue to benefit. And in this graph, that benefit is actually substantial. It's area A plus B. Area C and D would be the environmental damage that is done if there were no regulation. This is the individually rational amount of the polluting activity and therefore of the pollution. And if those externalities are not internalized in one way or another, that is what would happen, and there would be suboptimal levels of emissions. And then area C is the private benefit at the expense of the environment, at the expense of doing damage to the environment and damage to other people. Q prime is the optimal level of the individually rational level of emissions. Q star or asterisk, star is easier to say, is the optimal, the socially optimal level of economic activity. So there's a couple of, that is how you can interpret this graph. There is a few insights from this. The first is that optimal pollution is greater than 0. And people tend to get very cross as Kelsey here, when you say those things. Particularly if you say those things to a non-economist. The reason that optimal pollution is greater than 0 is because essentially the laws of thermodynamics imply that you can't do anything without pollution, right? And as long as there's a private reason to say use energy, you're gonna use energy and therefore emit sulfur and therefore emit CO2 and therefore emit volatile organic compounds and so on and so forth. That just follows from the fact that I mean, a lot of environmental pollution comes out of energy use, and a lot of environmental pollution comes out of agriculture, and food, transport, a warm house is to our benefit, right? And therefore there is pollution, right? And the only way to drive the pollution that comes out of agriculture to zero is to stop eating, right? Which most people would see as a suboptimal solution, right? Now there's two exceptions to this, or so people think. Actually one exception to this. If there is a simulative capacity, if we can emit a certain amount of pollution without doing damage to the environment, then intuitively some people say we should drive emissions to below that point. That is actually wrong. If there is a simulative capacity, that is, we can emit stuff without doing damage to the environment, then what happens is that the green curve, the marginal benefits of reducing pollution, shifts to the right, because pushing it below this point, this is the assumed simulative capacity, there is no damage, right? So that means that the curve translates to the right, and that just means that we can pollute more, right? Assuming that the curvature, that the slope of the curve does not change, right? So also, if there is a simulation in the environment, and there is always a little bit, optimal pollution is still greater than zero. And actually, the greater the assimilative capacity, the more we pollute, not the less we pollute. Okay. The other exception we're not going to talk about. We're going to talk about next term. I now see. I'm doing another lecture later today, and there I'm actually doing the second exception. That explains my confusion. So that was the first insight. Optimal pollution is greater than zero. Also, if there is a simulative capacity, and the reason that pollution is greater, that we find pollution that is greater than the optimal pollution, is because of the discrepancy between social and private welfare, because the externality is not internalized. Okay, second chapter. Let's look at stock pollution, where the environmental damage, where the emissions linger in the environment. That slide is there twice for some reason. This is what I want to do. The benefits of the polluting activity, I assume, still depend on the polluting activity. They depend on M. The damages of the polluting activity now do not depend on your emissions, M, but depend on the stock of emissions, A. And the stock of emissions I here set to a simple first order difference equation. That is, the stock at time t is the stock in the previous year, and there is some environmental degradation going on, 1 minus delta, so a fraction of last year's stock remains, but some of it remains, otherwise it becomes a flow pollutant again. But we add to the stock of pollution through our emissions in the previous period, right? So this is a first order difference equation. Now we define the current benefits is still, the net benefits is still the benefits minus the damages. So that hasn't changed, but instead of an M now we have an A here. And because it's a dynamic problem, we do not maximize net benefits, but we maximize the net present value of the benefits, right? So we this is still the same, right? But now we have to discount, and the discount rate here is rho, and we have to sum over all time periods. Now, the basic principle still holds that marginal cost should equal marginal benefits, right? Or the first partial derivative of this thing should equal 0. So if we do that, we make a decision at time t about our emissions at time t, so that's mt. So we take the first partial derivative of this thing here to m, that's dB dm. dA is not important in this case, and we have 1 plus rho to the power t there, right? Because the benefits of the polluting activity are assumed to be instantaneous, they only happen in that year. This doesn't change. The only thing that changes is that now if we look into the benefits in 2028, we need to discount it with 2 years to 2026, right? That is this operation here. The avoided damages of the pollution are now more complicated, right? What we need to do is take the first partial derivative of dA to m, and for that we need a chain rule, right? So we have dd, dA. So this is how damages change because the stock in that particular year changes. And then by the chain rule we have dA, dm. That is, how does the stock of pollution in year t plus s change if we slightly change emissions in year t, right? And of course that needs to be discounted to the year t. So we sum from s is 0 to the whenever in the future, right? So we kick 1 over 1 plus rho to the power t to the other side of the equation. That then becomes so we bring 1 over 1 plus rho to the power t to the other side of the equation. That means we drop out the t here essentially. So that is already somewhat simpler. Because I assumed that this is a first order difference equation. So if we put 100 tons of sulfur in the environment in 2026, then a year later in 2027, the stock goes up by 100. In 2028, the stock is higher by 1 minus delta times 100. And the year after that, it's 1 minus delta squared times 100, right? That is what is going on here. And that explains why this particular term, dA t plus s, dmt, transforms into 1 over 1 plus delta to the power s. This is essentially what remains of our emissions in the future. So this is nice. The next line is not strictly true, but approximately true. If delta and rho are small enough, then 1 plus delta to the power s times 1 plus rho to the power s is equal to 1 plus delta plus rho to the power s. Approximately, right? So we have a simpler equation here, right? We still cannot solve it. So what I'm going to do next is assume that the environment is in a steady state. That's always a very neat trick. Steady state essentially means that nothing changes, right? So what we have is that instead of having AT, we have A, because we don't need a subscript because nothing changed, right? So AT is A, so the first order difference equation becomes A is 1 minus delta times A plus M, which solves as M is equal to A is equal to M over delta, right? So now we know that. Of course, we also drop the subscripts here. So we have the B, the M, the D, the A, right? This is no longer varies over time because we're in the steady state, so we can bring this in front of the summation sign. Now we have a very simple term here. It's 1 over 1 plus delta plus rho to the power s, and you recognize that from your calculus as a power series. So this sum, provided it's an infinite sum, solves as this expression here, which you can rewrite as follows. We have A is M over delta, so we also know we don't know the A. But we do know the A, the M, so we can replace the D, the A with the D, the M over delta, times delta, sorry. So now we have solved it. And what you see is that previously we had that the marginal benefits of the polluting activity should equal the marginal damages of the polluting activity for the flow pollutant. Now we have that the marginal benefits of the polluting activity should equal the marginal damages of the polluting activity times a factor that corrects for essentially how fast the pollution is degraded from the atmosphere. That's the delta, and how fast we discount the future. That's the rho. So this term is here essentially turns everything into an annuity, right? So instead of equating the marginal benefits of the polluting activity to the marginal damages of the polluting activity, we now equate the marginal benefits of the polluting activity to the annuity of the marginal damages of the polluting activity, right? That is essentially what we've done. So that's one insight. The second insight is that instead of having rho, we essentially have delta plus rho. So essentially what we have is that we discount the future because it's the future and we discount money. The other thing is we discount the future because our pollution disappears through environmental degradation. So essentially the disappearance of pollution in the atmosphere and in the environment and in our waters essentially acts as a discount rate. Right? It's basically the same. So we discount the future we discount future environmental damage or the damage from our current emissions for two reasons. One, because the damage disappears through chemical and biological and sometimes physical processes. And we discount the future because we always discount the future, right? So far, so cost-benefit analysis. There's one important element here, and that is that we hardly ever know these things with any kind of accuracy. So I'm going to talk a little bit about uncertainty and what that will do to the analysis. Not a whole lot, but a little bit. So the classical distinction here, the classical terminology is due to Frank Knight, who you see here. And Knight, and this is still followed basically by all economists, and he wrote this in the 1920s. Knight distinguishes between risk and uncertainty, where risk is when you know the probabilities, and uncertainty, you don't know the probabilities. And the distinction here is that if you want to throw a die, not a dice, if you want to throw a die that is risky, because you know there is a chance of 1 in 6 of it landing on 3, say, whereas the time of Putin's death is uncertain, right? He will die at one point. Some people say he has died already, but you don't know whether it will be in 2024 or in 2029, right? And there's no way of estimating the probability of the time, the year of death of a single person, right? You can do it for a population with actuarial tables, but not for a single person. Since Knight did this, we introduced sort of a category in between, ambiguity, and the difference between risk and ambiguity is that in the ambiguous case, probabilities are disputed. Different experts would give you different opinions about what the probabilities are. I work on climate change, so that is where the example comes from. What you're looking at here are 9 different proposals of what the probability density of the climate sensitivity would look like. The climate sensitivity is how much the world would warm eventually if we double the atmospheric concentration of carbon dioxide. And Andronova, the late great Natalia Andronova says, well, the mode is somewhere actually very low, but then there's this big fat tail. If you listen to Forrest, then the mode is actually around 3 degrees, and so on and so forth. And both are very well respected climatologists, and they completely and totally disagree about what the probability distribution of this key parameter looks like. So this is ambiguity, right? We won't be talking about ambiguity today. We may be talking about it next term. Now, in the case of a risky situation where probabilities are known, you want to not maximize the net benefits, but the expected net benefits. And that follows from the axioms of von Neumann and Morgenstern. Von Neumann is the polymath that you see at the top, did a lot of work in mathematics, did a little bit of work in economics, also helped build the first atom bomb and everything. Morgenstern is a economist. And they published this particular theorem in 1944. And they argued that, no, they did not argue, they showed that if your preferences over lottery satisfy these 4 axioms, then you need to maximize the expectation of your payoff. The first axiom is completeness. That is, you have an opinion about everything. The second is transitivity. That is, if you prefer A to B and B to C, then you must prefer A to C. They also pose an axiom of independence of irrelevant alternatives. If you prefer A to B, then you must also prefer a lottery of A and C to a lottery of B and C, right? Because essentially what you're doing here is you multiply your A and your B by P, you make them smaller, but by the same amount, right? And then you add 1 minus P times C on both sides of the equation, so that is irrelevant, right? The payoff, if now becomes a composite lottery, but the additional term that enters in there just drops out of the equation, right? So this must be, this is a very reasonable axiom as well. And the final thing that they pose as an axiom is continuity. If you prefer A to B to C, then there must be a P where you prefer B to PA plus 1 minus P to C, right? Essentially what this does is it shrinks A, so the difference between B and A becomes smaller, and at one point you kind of like B more than you like P times A. You still like A better, but now you only get a fraction of that, right? Yeah, that's what's going on here, right? And then you also have a little bit of C that you also like not as much, but at one point this first term starts to dominate. For there is a P that does this, right? Now, if you think that these are four reasonable axioms, if you think that your preference ordering should satisfy these things, then you want to maximize not your net benefit W, but the expectation of your net benefit. In a discrete case, you take all possible net benefits and multiply them with the probability that these things would happen and sum over that. In a continuous case, you take the integral, right? You take the expectation. So previously I said that we put the optimum where the marginal costs equal the marginal benefits, or where the net present value of the marginal cost equal the net present value of the marginal benefits. In a situation where we have a lottery, where we are uncertain about the future, but we know the probability, so we're in a risky situation, then what we want to do in the static case is equate the marginal expected costs to the marginal expected benefits. And in the dynamic case, we need to add in the words net present, right? But conceptually, nothing has changed, right? Instead of equating marginal cost to marginal benefits, or the net present value of marginal cost and benefits, we now equate the expected marginal cost to the expected marginal benefits, right? Conceptually, it's still an equimarginal principle. Things change under uncertainty, things change under ambiguity. I don't think I will get into that next term. Things also change if you are in the dynamic situation, if you're learning over time and there's irreversibility, but that will be done perhaps by me, perhaps by Diego in the spring term, right? So this is a good place to stop or to take a break. After the break, I'm going to talk about alternatives to cost-benefit analysis. I'm particularly going to talk about multi-criteria analysis. And I'm going to talk quickly about how to apply cost-benefit analysis in practice. And I'm going to discuss that with a particular example, the London Super Sewer. I forgot to say about von Neumann Morgenstern that if you violate their axioms, you're subject to a Dutch book, which is jargon for heads I win, tails you lose, right? Dutch book is, of course, one of the many expressions in the English language that casts a bad light about my compatriots. A lot of people hate cost-benefit analysis because this notion of optimality, this notion of optimal pollutions doesn't sit well with people. Utilitarianism doesn't sit well with people. Main difficulty is that if you want to equate the marginal cost to the marginal benefits, they need to be in the same unit, typically money, and a lot of people are uncomfortable, and we'll talk about that at length, about expressing damage to the environment in monetary terms, right? So a number of alternatives have been developed. I think the most serious of these is multi-criteria analysis. And multi-criteria analysis always starts with eliminating the dominated alternatives, right? So we have three options here. The choice is between essentially badgers and cows, right? If you have more badgers in the country, then you also have more bovine tuberculosis. Badgers carry this particular disease, but they are immune to it, right? It doesn't do anything to them, they're just carriers. But if that jumps from the badger to the cow, then the cow gets very sick. It's very contagious, so you essentially need to cull the herd. So we have three options here, what to do. In option A, there's 250,000 badgers, but that with an annual infection rate of 25. Option B, there would be more badgers and fewer infected herds. Option C, there would be fewer badgers, but also fewer herds, right? So option A is just silly, right? If you like badgers, then you would rather go for B or different with C. If you like cows, you would rather go for B or for C. But nobody who likes both animals would go for option A, right? Option A is strictly dominated, right? So the first thing you do in cost-benefit and multi-criteria analysis, is eliminate the dominated options, the option that scores worst on all things that matter to you, right? So the choice really here is between option B and C, and in option B there's more wildlife, but also more damage to agriculture. In option C there's less wildlife, but also less damage to agriculture, right? So there is a clear trade-off. And what can you do in this case? Well, first thing you can do is just calculate the point, the break-even point, right? And the break-even point is fairly simple in this case. If we assume that one herd is worth more than 10,000 badgers, then we like C better than B, right? If we assume that there's 200 cows in a herd, then essentially if we say that one cow is worth 50 badgers, then we are indifferent between B and C. Right? So that is the second step in multi-criteria analysis. First step is throw out the bad options, right, that are just unequivocally bad. And the second is to say, well, this is the break-even point. And then what you can do is, do you think that a single cow, is worth more or less than 50 badgers? And you can invite a bunch of experts and say, what do you say? Is it 50 to 1? Then we're actually indifferent. Is it 40 to 1 or is it 60 to 1, right? And actually it doesn't really matter if it's 40 to 1 or 30 to 1, right? Because the break-even point is 50. So you only need to decide, is that number more or less than 50, right? And then you have your decision. You go for either option B or for option C. That is essentially cost-benefit multi-criteria analysis, right? Now this is a simple case. It gets more complicated if you're looking at multiple criteria and multiple alternatives, right? We're returning to the vegan question of last week that you may recall. We have dairy milk. Now the question is not where do we get the dairy from, but we suppose it comes from cows in this case, and we compare it to its alternatives, rice, soy, oat, almond. We look at emissions of greenhouse gases, I think. We look at land use in square meters, we look at water use, right? And clearly what you see is that if you care about the environment, whether it's emissions or land use or water use, you should switch to alternative sources of milk, right? Because on all three criteria, dairy scores the worst, right? It does most damage to the environment. But if you wonder, should I go for oat milk or almond milk, right? And if you care about climate change, then almond milk is better than oat milk, and also better than soy milk and better than rice milk. But if you worry about drought and depletion of fossil water, then oat milk and soy milk are much, much better than almond milk. Right? Almond milk is actually the worst of the four in terms of water use. It's the best of the four in terms of emissions to air. Land use, it's actually the second best option, right? It's harder to see because dairy dominates that, but the order there is rice is best, soy, almond is second, soy is third, and oat is fourth. And now it actually becomes, you have sort of multiple trade-offs going on, right? So it's no longer a question, is the number more or less than 50? Actually, we're now trading off in 3 dimensions, 4 options, and it actually becomes fairly complicated. You can still invite a bunch of experts and say, how do we weigh climate change against depletion of groundwater? But it is a much more complicated question, right? And obviously the trade-off between what kind of milk you drink doesn't just depend on its pressure on the environment, it depends on the price, it depends on the taste, it depends on whatever sort of metabolical, is that the right word, needs you have, right? A good thing about dairy milk is that there's lots of calcium in, and if you have weak bones or if you're growing, then you actually need the calcium, right? The other milks have different advantages, also different tastes, right? So different people may choose very, very different. But you can sort of like see how complicated this quickly gets, right? But that is multi-criteria analysis. Multi-criteria analysis is still very technocratic. It sort of says we, instead of inviting an expert to do a cost-benefit analysis, we invite an expert to do a multi-criteria analysis, and as part of the multi-criteria analysis, other experts may be consulted. Same is true for cost-benefit analysis, but it's a very technocratic approach to things. And politicians do not always like technocracy, because then essentially they give their job away, right, to somebody else. So there's a whole bunch of other alternatives that have been suggested, and the order is still wrong. The first one, common in things that relate to human health, are so-called safe minimum standards, where essentially we say we forbid everything that could do damage. You may think, well, this is actually a reasonable thing to do for, say, additives to food, right? We don't want stuff in the things that we eat that give us cancer, right? I guess we can all agree on that. And then essentially you want to bring sort of the concentration of this carcinogenic material to below a certain threshold. And that sounds all very objective and stuff, but it is in fact not. The way we do this is that we take a substance that we think is potentially toxic, we feed it to 1,000 rats, see how many of the rats die, and if that's less than 0.5%, then we say this stuff is safe. Because less than 0.5% is an acceptable risk for rats, and of course we are 100 times bigger. So a fatal concentration for 0.5% of rats is fatal to 0.05% of humans, right? And then we declare it safe. That's how this stuff is done, right? Is that right? Is the rat the right animal? Do we want to try it on mice instead? Is 0.5% the right number? Who knows, right? It is fairly arbitrary. Related to this, what politicians often do is, instead of a safe minimum standard, they proscribe the best available technology. That is, you need to shape your production process such that it is the highest possible standard. And that is how we're going to clean up the environment. We're not going to discuss really about to what extent the environment should be cleaned up. You should do the best you can. Problem with best available technology is that if you ask engineers to come up with the best technology, they get very excited and design a very complicated thing that is extremely expensive, but also very clean. So typically this is qualified as best available technology not exceeding excessive costs. And then again it becomes sort of arbitrary what is deemed excessive and what is deemed not excessive. And if you believe the Trump administration, right, any cost of anything that would help the environment is seen as excessive, right? Further related to this, the safe minimum standard, best available technology, is the so-called precautionary principle. There's a lot of confusion about what this really means. One interpretation of the precautionary principle is that uncertainty is no excuse. That is, if you're not fully certain about the benefits of your action or the costs of your action, there is no reason not to do it. I think that is a very lame interpretation because this basically goes for everything, right? If you decide to study economics, you can't, at the point you make the decision, you can't fully know what your career will be like, right? That's impossible to know. If you decide to marry somebody, you don't know what they will be like in 20 years' time, right? It's impossible to make any decision if you say, I'm going to wait till I know all the consequences in full of my decision, right? If that is your rule in life, then you never decide on anything, right? So the other interpretation of the precautionary principle is that it's better to be safe than sorry. That is just risk aversion, essentially. The problem with the precautionary principle is that it's often abused to stop progress. So this is particularly the case in the regulation of pesticides. So there are pesticides on the market, right? And now companies are putting or asking for permission to market new pesticides. And on the current legislation, if you want to bring a new pesticide on the market, you need to go through a whole bunch of tests, that is right and proper. And if there's a little bit of doubt that that particular proposed new pesticide might do harm to the environment, then the precautionary principle is currently interpreted in European and British regulation is that we're going to forbid this new pesticide. Now, that may seem to you as that's a reasonable thing to do, right? Because it's better to be safe than sorry. The problem with using the precautionary principle in this way is that you do not look at the counterfactual, or in this case, the factual, right? The counterfactual is we permit this new pesticide, The factual is that we continue to use existing pesticides. And the question is not whether the new pesticide might do harm to the environment. The question is the new pesticide, is that going to replace all the pesticides that do more harm to the environment? That would be, I think, a better criterion. Is the new alternative better than the existing ones? Rather than, is the new potentially dangerous, right? That's the current rule. So that's a precautionary principle. Another thing that is particularly popular recently are so-called citizen juries. I think it's a total cop-out. Essentially, you go back to a multi-criteria analysis, but instead of having an expert decide how to weigh the three different criteria in this case, you essentially invite a number of randomly selected residents or citizens of a country, and you let them study the material, you let them discuss, and then they will tell you what to do. There are sort of advantages to this in principle. This is the old Greek style of democracy. There's also disadvantages to this. I think it's a cop-out. We have elected a parliament to make difficult decisions. So why is it outsourced to another body? I just don't understand. Another problem that you have with citizens juries is that they can be captured by experts who are stealth advocates, that people go in and say, this is the truth and you should believe me and you should not believe these alternative experts. I may actually know better, but I am a smoother talker, so you should follow me, right? These processes can be captured. Finally, you could also just put the question to everybody in society through a referendum, right? And well, you guys are, most of you are English, and you know about referendums and what they can do. Most standards for the environment, as well as for many things, are essentially arbitrary. From an environmental perspective, from an economic perspective, they're essentially just the result of political bargaining. Whoever holds the balance of power in Parliament at that particular issue decides what the standard is without necessarily any rhyme or reason other than power play. So these 5 or 6 or 7 alternatives are not very economics. Economics comes back into play once a target has been set. You can ask the question, how do we meet that target at the lowest possible cost? That is not cost-benefit analysis, because the benefits do not play a role. That is cost-effectiveness analysis, right? And it's important to keep those two separate. Cost-benefit analysis is about how do we set the optimal target. Cost-effectiveness analysis is, given a target that may or may not be optimal, how do we reach it at the lowest possible cost? Obviously, in cost-benefit analysis, you still want to reach the target at the lowest possible cost, right? But the target itself is also part of the analysis. In cost-effectiveness analysis, it is not. Now, there is a lot of confusion about cost-effectiveness analysis, and the most common is the use of the word cost-effective as a synonym for cheap. That is just wrong. If you use the word cost-effective like that, you just signal that you did not pay attention in class, right? Actually, a lot of people are signaling that. So cost-effectiveness analysis, you meet the target at the lowest possible cost. So you cannot be more cost-effective, right? You cannot be more at the lowest possible cost. So whenever you read in a document that this proposal is more cost effective than another, the writer just signals, I don't understand economics, I don't understand mathematics, I do not speak English good. That's essentially what they're signaling, right? So don't fall in that trap. Sometimes, particularly amongst people who have German or French as their first language, people use the word cost efficient rather than cost effective. Cost efficient is just the dual of cost effectiveness analysis. If you don't understand what I just said, don't use the word cost efficient, right? Okay. If you want to say that something is costless, then we have a perfectly good English word. You can say it's cheaper, right? It actually has fewer letters to spell as well. Okay, 30 minutes left, right? Yes. I'm going to talk about applications of cost-benefit analysis. I'm going to look at some past, and then I'm going to focus on the London Super Sewer because things are much more concrete when you talk about a particular example. So, social cost-benefit analysis. So cost-benefit analysis is just project appraisal, but now for society rather than for a company. That's another way of putting it. And the difference between a cost-benefit analysis for a company and a cost-benefit analysis for society is that you include things that happen outside the company. So you also look at what do I do to the rest of the society, and in the environmental case, what do I do to the environment. Social cost-benefit analysis was pioneered by John Crutilla, who you see here. And essentially what you need to do is you need to systematically count and value everything that is relevant to the decision, right? And relevant to society. And benefits are then anything that increases human welfare, and costs are anything that decreases human welfare. There's various ways of doing this. If we have a single project, then the question is simply, are the benefits greater than the costs? If you have to choose between multiple discrete projects, then you rank them according to their net benefits, and then you begin by picking the most profitable one, and then move to the next one until you run out of money to fund them, right? That's essentially what you do. Of course, if you can borrow money, then you should actually fund everything that has a positive benefit or a benefit cost ratio greater than 1, right? Is what I should say. How can you use cost benefit analysis? You can use it for overall environmental policy. You can use it for specific projects, environmental management. Some of the projects to which it has been applied, I'm going to talk about this one. I forget which dam this is, the London Olympics. HS2 is another prominent example, the introduction of new pesticides, that's what the B does, or the development of new oil fields, right? This is of course an old oil field, we don't get oil out of the ground like this anymore. And you can do this before the fact or after the fact. Exposed cost-benefit analysis have fallen out of fashion, perhaps because the results are sometimes devastating for the people who would like to know the results. So Robert Hahn is a champion of this, but Robert is getting old, so he doesn't do this as often anymore. But in 1996 he published a paper looking at environmental regulation in the United States between 1990 and 1995, and he found that only 50%, that is half, actually had benefits that exceeded the costs. And the rest, he just could not find the justification. David Pearce did a similar exercise, not for the US, but for the EU, looking at the environmental directives of the European Union, and we were still subject to that at that time, and still actually at the moment. For many of them, found the very same results. These things cost a lot of money, but it's very hard to find benefits that justify these things. And that it may be one reason why these things have fallen out of fashion. So Peirce is no longer with us. Hahn he must be almost 80 now. Maybe I'm overdoing it, maybe he's 75. But because there's no funding for this, because the regulator doesn't like the results, there is no more recent literature on this. There are, of course, all sorts of problems with cost-benefit analysis. They may be systematically biased. One thing, again, I'm sort of the examples that come to mind are what the Trump administration is doing at the moment. And one of the new rules that came about a few weeks ago is that essentially they are no longer counting the effects of federal regulation in the United States on human health. That is no longer important to them. And that, of course, shifts the balance towards all sorts of stuff that make you ill, right? That all of a sudden, where previously it looked bad because it gave a lot of people cancer, now because we no longer count cancer, it looks like a much more attractive project, right? So there's definitely things going on there. Another reason why cost-benefit analysis may be biased, I should not do this, is that there are other goals in life beyond efficiency. Efficiency is a very utilitarian, narrow utilitarian process, right? So it's about the distribution of these costs and benefits. We talked about actual and potential Pareto improvements. In this case, if a project passes the cost-benefit test, then essentially what you say is it is good for society as a whole, which does not mean that it's good for everybody in society, right? And then you can think of compensation through the benefit system or the tax system or what have you. One argument that some economists make is say, well, we should not worry too much about distributional issues because if you do a great many projects and we do a cost benefit for all of them, then they will all benefit society, and some of these projects will hurt one particular group, but then another project will particularly benefit that group. And it will come out in the wash, and if you do a great many cost-benefit analysis for a great many projects, then these equity arguments wash out. So what we're actually going to talk about in Week 10 is that no, this is not true. There are there are groups that are systematically disadvantaged, and regardless what you do, they always come out at the bottom, right? Okay. What are the steps that you do in a cost-benefit analysis? The first is you need to come up with why do we want to do this, right? Then second, you need to come up with what could we possibly do. And also, if we don't do anything, because that is always an option, what would happen, right? The third thing is, who are we going to look at? Who are we going to include in our cost-benefit analysis? Are we going to draw a small box or can we draw a white box around our project? That is what matters. Then once you have made those three key decisions, you need to identify all the potential costs and benefits. You need to predict the size of these costs and benefits. You need to attach money to that. We're going to talk about that next week, the week after, and the week after that. Typically it's dynamic, so you need to discount everything to today, add it all up, calculate net benefit analysis. By that point, you have made thousands of assumptions, typically. So you need to do a sensitivity analysis on, if I change this assumption a little bit, do my conclusions drastically change? There's no. And then once you have done all that, you can make your recommendation, right? Now this all sounds too abstract, so I'm going to take you through. No, I'm not going to take you through on the super sewer because that would be very distasteful. I'm going to take you through the example of the London super sewer. This is a project that started around 2013. And it is very simple. London sewers were built in Victorian times. There is now, the city has completely changed, and there's many more people in the city, and the old system simply is not up to the task. And one big problem is that if it rains heavily, because rainwater is not separated from wastewater, if it rains heavily, the sewers get essentially overwhelmed, and the shit may end up in people's houses, may end up in people's gardens, may end up in the street, may end up in the Thames. It is a big mess, right? So the question is what to do. So the rationale for that, I actually gave you the rationale. London's Victorian sewer system is simply not up to the task anymore. That creates all sorts of problems. It smells, it looks bad. This is David Williams, who you probably don't like. I am actually old enough to recall the time when he was funny, but that is a long time ago. But for some reason that only he can think of, he decided to go swimming in the Thames. And even though he looks cheerful in this picture, he actually got violently sick after. Because you should not ingest human excrement. That is not a smart idea, right? And that is what happens if you swim in the Thames, right? Not just swimmers, but also rowers and everything. Fish don't like it either. Here you see an example after a particular heavy rain of fish kill further downstream, where just thousands and thousands of fish were killed and ended up on the shores of the Thames further downstream. So yes, something needed to be done. The thing that they suggested doing is to build what is colloquially known as the London super sewer. The light blue here is the Thames. And the idea was to build a big tunnel, and I'll show you a picture of the size of the tunnel in a second, under the Thames that would essentially carry all the wastewater. From this point it would carry it downstream towards treatment plants that are here, and a pumping station that is here, and another treatment plant that is here. From this point on, things would be ported upstream to treatment stations further along, right? So this is a fairly large engineering works. The tunnel that they're building looks like this, right? You can drive a car through. So this is big infrastructure. Essentially they had the plan that I showed you. It was the plan that they eventually decided on. They looked at 24 different permutations, new treatment plants versus upgrading existing treatment plants. Do we put in smaller tunnels in more storage, or bigger tunnel and less storage? All that needed to be decided on, and essentially they had 24. They had engineers sort of designing 24 alternative systems. There is, of course, a 25th option, and that is not to build anything and just continue the current situation, where you have these risks to fish, you have this risk to David Williams, and there's also costs of cleaning up the stuff, And essentially what they did was they had little boats going along the Thames, essentially fishing stuff out of the water. If you were looking for a nice job, then this would be an option, right? It pays very well, but it's not the most pleasant thing to do. Okay, it's an old joke there. Second question, or the next question that you need to decide is who matters? And this is actually a difficult decision. Typically what we would do is that if we do this at a national level, then it is everybody who resides in a country counts. There are, of course, politicians, Theresa May is one, and Keir Starmer is another, who says we should only count citizens. So people like me, and I guess a few in the room, who do not hold a British passport, we don't count, right? But people with a British passport who live in Switzerland do count, right? Which is a peculiar thing to say, Sir Keir. But that's politicians for you. In this case, it's a local project. It's not a national project. So initially, what they did was they only looked. Initially, they only looked at people who lived within the M25, the circumference of the M25. When they did that, they actually found that this was not a good idea because a lot of the stuff is dumped outside of the M25. But also it was a particularly bad idea because some of the treatment stations were built in Surrey, outside the M25. So these are obviously people who have standing. So the first cost-benefit analysis, they looked at M25, but the final cost-benefit analysis, after a lot of protests, they said, look at people in London and the southeast, right, where a lot of the stuff is going on. An important thing here is also you should include all the people who are going to pay for this. In this case, the costs are carried through the water bills. So people in Scotland do not pay water bills for London, so they do not matter, right? So they can be excluded. But everybody who is a customer of Thames Water does have standing because they will pay for this project, or they are paying for this project, right? So these are important considerations, right? I have a project, I draw a box around my project, and what I leave in and who I leave out actually matters, right? The green bits are the benefits that were included. So the avoided cost of those boats that were fishing for shit is included. In terms of environmental things, they looked at the visual amenity, less litter in an important tourist spot, fewer health risks and fewer fish kills. They did not, in terms of costs, they looked at the capital expenditure and the operating expenditures, so capex and opex, right? That's what you should be looking at. They did not include, or they did include, they looked at the noise and disruption during construction. They looked at the energy that was used for the construction. Things that are not on this slide are not included. Right? So it's not just fish that are killed, but also frogs. And the frogs don't matter, right? They only looked at fish kills in the Thames estuary. Stuff that happened in the North Sea doesn't matter, right? Particularly that would be algae blooms and those sort of things. So here are things that they did not look. Actually, I have a whole list here of things that they did not look at. Other things that they did not look at is you have heavy construction. If you're drilling a tunnel under London, you're going to create damage to heritage, right? Old buildings, cathedrals, abbeys, that sort of stuff. They did not consider the sort of archaeological disruption that they would create, right? Step 5, quantify all the impacts. That's what they've done. The complexity of this should not be underestimated, right? So they had 24 alternative projects plus the status quo, so 25 scenarios. They looked over 50 years, and then they needed to estimate the number of fish kills, the number of people falling ill for all these alternative projects for 50 years, right? So it should not be underestimated how much work goes into this. And then, of course, there's people like me bitching on the outside, but you did not look at the frogs, right? And you did not consider the birds, right? This is a major piece of work. Important thing in estimating capex and opex is optimism bias, and that's what you see in this table. Engineers are, whenever they bid for a project, are extremely optimistic about what things will cost, and then eventually there will be cost overruns, right? And that is almost always the case. There's never a project that is ever delivered on time and at cost. And you can say, well, that's because engineers don't know how to count, and that would be a silly thing to say because engineers do know how to count. This has to do with the incentive structure. So the government sort of wants to procure a particular project and then invites bids from 5 engineering companies, and they give it to the one who gives the most value for money. So it is in the interest of the engineers during the bidding process to be as optimistic as possible, right? And say, we can do it for 100 million. Those suckers there, they will charge you 150 million, but we can do it for 100 million, right? So it goes to the company that bids the lowest, right? And then you enter into a long-term contract with that particular engineering company. And then it's actually costly to walk away from the project, right? If the project is halfway through and it turns out to be more expensive than they initially bid for, then actually there's a sunk cost and there's embarrassment and everything, and then you allow the company to begin charging the real price, right? So it is actually part of the bidding process that makes that the initial projected cost is much lower than the eventual cost. His Majesty's revenue has actually estimated that typically the optimism bias is 24%, for standard buildings can go up to 50%, equipment and development actually it can go up to 200%, right? They say we can do it for 100 million and then it will cost 300 million. So that is an important thing to keep in mind. Then all these things need to be monetized, or the non-market things need to be monetized. This is the numbers that they used. Sewage litter is anything that ends up in the sewer costs £1.82. Health risks were valued at 38 pennies per day. Fish kills were counted at £1.51 per event, right? We're going to talk about it next week and the week after where these numbers would come from. Discount everything to today, net present value. You know that. You also know just how powerful the interest rate or the discount rate can be. So if we invest £100 today at an interest of 2.1%, that is worth £800 in 100 years' time at investment an interest rate of 10%, that is 1.4 million, right? Vice versa, if our interest rate is 10%, then 1.4 million in 100 years' time is worth only £100 today, right? And if our interest rate is 2.1%, I don't know why George picked that number, then £800 in 100 years' time is worth £100 today, right? So discounting is extremely important. Add up everything, and they found that the net present value, depending on the project and depending on how you exactly pick the parameters, was something like 3 to 5 billion. They did extensive risk and sensitivity analysis. This is a quote from Eldred. Blah, 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 blah. The outcome of the CBA or other quantifications will have misleadingly reassuring precision. Decision makers may understandably take this precision to mean that they can confidently rely on the recommendation of the CBA, when in fact it is no more reliable than the dubious numbers on which this is based. This situation is reminiscent of an apocryphal story about weighing hogs in Texas. Down there they put a hog in one pan over large scales and put rocks in the other pan until they exactly balance the weight of the hog. Having done that very carefully, they guess how much the rocks weigh. Which is a bit of a cynical way of describing CBA, but not too cynical, right? So there's all sorts of things that can go wrong. We can exclude the frogs and the birds. We can mismeasure these things. That are simply measurement errors. And particularly, we're not talking about things in the past. We're not talking about what was London like after we had built a super sewer. No, we are talking about what will London be like after we build a super sewer. And what will London be like in 2070, right? Not what was London like in 2017. So there's all sorts of assumptions that go in there. There are, of course, also political pressures on this. And people sometimes misinterpret what is going on. There's a lot of people who say that the people who do cost-benefit analysis are swayed by politicians to come up with a favorable number, a number that is favorable to the politician. That doesn't happen that often. It happens sometimes, but it's actually fairly rare. Much more prevalent is that politicians hire the consultants who they know will give a certain answer, right? So consultants come with a reputation. Some are more conservative, some are more green, some are more socially minded. And over the years, they have done many projects, many cost-benefit analyses for various governments and government agencies. And they build up a reputation that this company will always lean towards the environment and that company will always lean towards industry. And that means that a conservative government will hire the latter consultants and then just let them do their work, but the bias comes in at who you hire rather than that you lean on consultants. Because if you lean on consultants, then that gets out in the press, you have a big political scandal, but in the process of selecting who is going to do this work for you, that is much more secretive, much more discreet, and that is how pressure or how things are steered in a particular direction, right? And then finally, a decision is made, right? 2 minutes left. So, as I said, the original cost-benefit analysis said, no, don't do this. Then they revised it and said, yes, do it, right? The main reason that they did not want to do it because of the increase in the water charges. The thing is now operational and has been operational for a year or so. I actually forget the exact date when it became operational. And if you want to know more and look at other pretty pictures, go to Tideway London to see all the wonderful things that they have done. That's it for today.